Welcome AP Physics, Electricity, and Magnetism students. Today we're going to be reviewing conductors and capacitors. The topic will be a little bit different today. In the previous topics I really tried to just show the main ideas and not get bogged down into too many details, but I found in creating the notes for today that doing that did not really create a cohesive kind of statement in terms of the physics involved. So this, some of the proofs today, I'll be taking more from like start to finish, showing every single step. So it'll be a little bit more lengthy, but otherwise the some of the derivations didn't really make much sense, presenting them in too much of a skeletal fashion. So what we're going to be looking at today are the topics here, the properties and behaviors of conductors in equilibrium, and then also capacitors, a general view, and then we're going to look at three different geometries, parallel plate, spherical, cylindrical capacitors, deriving the expressions for the capacitance of each of those, and then I'm going to talk a little bit about dielectrics. So that's what's coming. Okay. Alright, so we're going to begin, as I just mentioned, properties and behaviors of the conductors in equilibrium. Now, I just want to emphasize the equilibrium part. We're going to see certain facts, like, for example, that the electric field inside of a conductor is zero. That is only true in static equilibrium. In the next topic, circuits, we learn that, or you learn that the electric field is maintained in a conductor that's conducting electricity, and that's because a battery is hooked to that conductor, that wire, and the battery maintains the voltage and therefore an electric field throughout the conductor, which makes charge flow through it. What we're talking about here is different. You dump a bunch of charge onto a conductor and then you just let it reach equilibrium. That happens very quickly, less than a second, less than a millionth of a second. It quickly establishes equilibrium. And then what happens is the electric field is zero inside that conductor in static equilibrium. Also, that's true even if you bring another charged object near that conductor. The electric field will still be zero inside the metal and inside any cavity inside that conductor. Why does that happen? Well, I colored this pink, and this positive creates an electric field pointing everywhere away from it. So you see these arrows. If the conductor was not here, the electric field would have these directions in these regions of space. But what happens is you put the metal there, and then that creates a force, F equals QE on the electrons. Now, if the electric field points that way, the electrons feel a force this way. So they start migrating to the left, and they build up on this surface over here, leaving a bunch of protons that they used to be orbiting alone here, so we have a net positive charge on this side of the conductor. And that then creates an electric field from plus to minus. So while the original electric field is to the right, the metal itself within it and in the cavity makes its own electric field, perfectly matching this rightward electric field, balancing out, in other words, adding to zero. Okay, and that charge moves until that happens, and there are no more forces, and then the conductors, the charges within the conductor are in equilibrium. So that only works for conductors because, again, these minuses came from the atoms over here. In a non-conductor, they would not be free to move all the way through the metal or the object to settle over here. The other thing I want to point out is that this sphere here, we're looking at a cross-section, is attracted to this. That also happens even though this conductor is neutral. Notice there are 6 positives and 6 negatives, so the Q is 0 on this conductor. It's still attracted to this charge over here. And if you just look strictly at Coulomb's law, F equals KQQ over R squared, you would say, well, wait a minute, this has a Q of 0, so shouldn't it have 0 traction to this object over here? Well, the reason why that attraction occurs is because these minuses here are closer to this charge than these pluses. So when you do KQQ over R squared for this electron, you get a certain attraction. the repulsion here between this positive and this positive is less because of the larger radius involved. So we have less repulsion than we have attraction here. The net effect is that that sphere will be attracted to that positive or negative. Same thing if that were negative. But, okay, so fact one, electric field 0 inside the conductor. Second fact that you have to know is that the electric field is perpendicular to the surface of a conductor. And again, that's always in when the conductor's in static equilibrium. And so the reason why it's related to this up here, that if there were an electric field that were not perpendicular, say it were going like this, then that would mean there's an electric field component that points along the surface, and electrons would then migrate and move to the right, creating an electric field that cancels that tangent component. So not only is E 0 everywhere inside the conductor, it is also electric field along the surface is perpendicular to the surface. This is just using Gauss's law to show that you could find the charge density at any point along a conductor if you knew the electric field. By you make a little Gaussian surface here, and the only flux through this Gaussian surface is here, because these are running, the electric field is running along these surfaces, so there's no flux in these two surfaces, and there's no electric field in here, so there's no flux only in this surface, E times area right there, and that's going to equal Q enclosed, the sigma times area right here, enclosed in our Gaussian surface over epsilon 0. So the electric field right at the surface of a conductor is always E equals sigma over epsilon 0. The other fact that's in the curriculum that you need to know is that the conductor, the whole metal, is in equipotential. Again, that's only true in static equilibrium. That means equipotential, the whole conductor is equal voltage everywhere. So there's no voltage difference anywhere. I should have put delta V equals 0 here. And the reason why is this is the definition of voltage. It's the negative integral of electric field dot dx along any path. Inside the conductor, like in this region, this integral is 0 because there's 0 electric field. So there's no voltage difference between any 2 points inside the conductor. It's also, this integral is 0 along the surface, because if you integrate along the surface, then your dx is perpendicular to the electric field, and that makes the dot product 0. So you get a 0 answer for the voltage going along here for different reasons. Yes, you have electric field, but 90 degrees to the displacement. So the surface, the inside of the metal, all of the same voltage, an equipotential, we say. Okay, so an example calculation that sometimes appears on the AP is if you have a couple spheres and one has a radius of A and the other one has a radius of B. And this one has a charge of Q0 and this one has no charge. So that's the initial situation. You connect these with a long wire and they're pretty far apart. What happens is charge will come off of this conductor and go over to this conductor. That'll continue until the voltages are equal. In other words, 10 volts and 10 volts or something like that. So the voltage is equal when KQ over R is, that's what voltage is, KQ over R for a sphere. So the charge on this sphere is the original charge minus whatever charge went over to this sphere. And then what charge is on this sphere is just Q. And then so with the radii A and B, you could solve for the two charges. So that's a quick setup of how you would figure out the charges on each of the two spheres after they're connected with wire. The other fact about conductors in static equilibrium is that all the charge is on the surface of the conductor. In other words, if I dump a bunch of electrons here, they will rush out and settle on the surface. Here's the proof of that. If you use Gauss's law and you make a Gaussian box or sphere or whatever you want inside that conductor, we know that the flux has to be 0 because the electric field is 0. And so the left side of the equation here is 0. Well then, the right side has to be 0 also, and that means Q enclosed is 0. Also, you need to be able to sketch electric field line diagrams for conductors in various arrangements, different patterns. So this is a charge within the cavity of a conductor. So this could be like a hollow metal. This is all metal. And then there's a hole here filled with a vacuum, and then we put another sphere that's positive in the middle. This is the electric field line diagram, as well as it shows the charges, how they settle on the shell on the side. But now the shell is neutral. So the electric field symmetrically comes out of this positive. So within the cavity, you can have an electric field if there's a charge in there. If there's a charge outside, then no. Like we said over here, the electric field is shielded away. There's no electric field in the cavity if there's no charge in it. But if there is, then there is. There is an electric field. So notice the symmetrical pattern. And then what happens is the electric field is 0 inside the metal. And the reason why is because this positive makes an electric field pointing away from it. That makes electrons migrate and try and get attracted to this positive. But they get to this surface and they stop. They cannot jump the gap. So they settle on here. And what that does is it shields the effect of this charge. If you make a Gaussian surface like this, we've got the same amount of charge positive as negative enclosed, and so that's why the electric field inside the metal is 0. But where did these electrons come from? They came from atoms on the outside. So when this electron migrated in, it left a proton by itself without a partner. And so we've got an equal distribution of unpartnered protons on the outside. If you count the minuses, there are 12 of them, and there are 12 positives. And then the electric field, once we come out here, if I make a Gaussian surface, I still have the net Q enclosed of the inner charge. And so the electric field lines continue. Notice that the electric field line pattern out here is the same as in here. It's as if this metal shell was not even here. So putting a metal shell around a charge does not eliminate the electric field outside. And in fact, if you were a little proton or electron moving around here, you wouldn't even know there's a shell over here. The electric field would be the same as if that charge were all by itself without a shell. So that's all the electric field does, is it interrupts, the metal does is in the shell, it interrupts the electric field. All right, another fact that you need to know is that if we move that charge inside that cavity, the electric field out here is unchanged. Oops, I'm going to move that down. So as you can see, the E out here has the same pattern as here. Symmetric 12 electric field lines. But by moving this off center, it distorts the electric field in here. Why? Remember, electric field always has to be perpendicular to the surface of a metal. And if I drew this electric field line straight out, let's see, what would be a better one? This one, straight out like this, or this one, you would see that when it hits this surface, it does not hit at a 90-degree angle. Right? 90 degrees is like this. It's hitting at a different angle. So this field line has to curve so that when it gets to the surface, it hits at a 90-degree angle. And that's what happens with all these. They curve so they touch this inner surface at a 90-degree angle. And what that means is now the minuses that were formerly evenly distributed over here are now more concentrated over here. And so there's still 12 minuses like over here, they're just more concentrated. The E in this cavity is still 0, even though I move this off-center. And that means that the off-centered location of this positive is shielded out here. In other words, if there's an atom here, it cannot feel the effects of moving this around because there's no electric field caused by that, shielded by the minuses. And that means these pluses remain symmetric. So that's an example of how conductors, one of the effects that when this charge moves around in the middle, it does not affect the electric field out here. All right, well, conductors can be used to make what we call capacitance. A capacitor is just two metals next to each other. So I forgot to bring a couple metals but I've got a couple blocks of wood here. Let's suppose this was a metal and this was a metal. I'd have myself a capacitor. I could hook this to one terminal of a battery and this to another terminal of a battery. This would become positive and this would become negative and they would be attracted to each other. So you could have any kind of shaped capacitor you want, but what it is just two metals next to each other, each one hooked to a different terminal of a battery. Okay? But in general, we have more, nicely shaped capacitors. I'm going to talk about that in a bit. But what does a capacitor do? Well, I have a little circuit here to illustrate what happens. So there's a switch here that can flip either between point A and point B. If I flip this into A, then the top of this capacitor becomes positive because it's connected to the positive terminal of the battery, and this becomes negative because it's hooked to the negative terminal of the battery. So the capacitor charges, and I put charges in quotes because the capacitor still has overall a neutral charge. If this is positive 2 coulombs, this is negative 2 coulombs. So overall Q is 0, but when we say it's charged, we're just talking about the charge of one of the plates, okay, versus both of them being neutral. But it also stores charge and energy, okay, because when I flip the switch to position B, the capacitor discharges. The current goes around and goes through this bulb and lights it up, and light is energy. It also makes heat. So that means the capacitor released charge and energy into the bulb. Now, this is the basic definition of what capacitance is. C equals Q over V. And what it is this ratio remains the same for any physical capacitor. So 1 farad, so coulomb per volt is a farad. So let's suppose I have a 1 farad capacitor. The more volts I put on it, the more charge is stored in that ratio. No matter what battery I hook to it, always is 1. So it's a 1 farad capacitor. This is just that same formula rearranged, showing that for a given capacitance, the more volts I put on, the more charge the capacitor stores. And these are the formulas for the energy stored in a capacitor. Remember that normally voltage is QV. That's only if the voltage remains constant for all the charge passing through that voltage. But since the capacitor loses volts as it loses charge, that's what you have to have that one. You have to integrate basically to get these energy equations. But we're going to skip over that. More than enough details for today. All right, so moving on. So all right, now a common thing in this topic is that you have to derive the formula for the capacitances of various geometries. So for example, the parallel plate capacitor, you have to be able to derive this C equals epsilon 0 A over D. A being the area of one of the plates of the capacitor, D, oh I forgot to put it in here, how far apart the capacitor plates are. So that's D right there. Okay. So the pattern for parallel plate, cylindrical, or spherical capacitor is you always find the electric field first, then the voltage, then the capacitance using C equals Q over V. So the way we find the electric field in a parallel plate capacitor, we use Gauss's law. We make a little Gaussian surface here, enclosing a portion of the charge of the positive plate. So E times the area of the Gaussian surface. What you need to know is that the only part of this that has flux going through it is the bottom right here. So I tried to color coordinate it. It came out kind of a little greenish red. Okay, so that's the E times area down here. And then that's going to equal Q enclosed, which is sigma times area. The sigma will be total charge over total area. And then I multiply by the area, the portion of that area trapped in our Gaussian surface right there. So I try to color coordinate blue and blue, though it doesn't show up that well. And then that's all over epsilon 0. The Gaussian area goes away, gives you the electric field. The voltage, now, normally voltage, it's the voltage is the minus electric field integrated from one point to another. But because the electric field is a constant, we're welcome to just use electric field times distance. So there's the electric field times distance. Then finally, we can get the capacitance by plugging in the charge, which was Q, right from the start, and then the voltage that we just derived. Flipping that over gives us the expression for the capacitance of a parallel plate capacitor. Okay, so you have to be able to derive that. Electric field voltage, plug it into C equals Q over V. And we have to do that for spherical capacitors also. Okay, so following that same process, 1, 2, 3, we find the electric field. Now, okay, so this is the spherical capacitor. We got one plate or sphere within a sphere, another sphere. This inner sphere has a radius A, this has a radius B. Doesn't always have to be the case. We could have R and 2R, something like that. But the point is that you know those parameters, those dimensions of the capacitor. We use Gauss's law to find the electric field. That's simple for a sphere. Q enclosed is just the Q of that sphere, and that gives us the electric field there. Next, we're going to find the voltage. Now that we have that electric field, we want that because we want to find the voltage for C equals Q over V. So again, voltage is negative integral of electric field from one point to another. So negative, here's the electric field. I wrote it as r to the minus 2 just to make the integration easier. And I go with limits B to A. I want to go against the electric field to get a positive answer for my voltage, because you can't really have negative capacitance. So the electric field points away. I'm going to integrate in from B to A, so I get a positive voltage. So you add 1 to the exponent, which makes minus 1, and then you divide by that new exponent. The minuses go away, and then you plug in the limits. 1 over A minus 1 over B, common denominator there, B over B, A over A, combined there. And now we have an expression for the voltage, which we can now plug into C equals Q over V again, like we did over here, but a different expression for voltage for the spherical capacitor. Q's go away, as they always do in these capacitor calculations, and there's the expression for the capacitance of a a spherical capacitor. The next geometry, you could have a cylindrical capacitor. What that means, it's really a cylinder within a cylinder. I got a little scrunched here. If I were doing this on a computer, I would move it down a little bit, but I drew it, and then it was too close to the top, I left it there, rather than redraw it. But we have an inner cylinder and an outer cylinder. So there are the two plates, right? Two metals. That's what a capacitor has to be, two metals. The inner conductor has a radius of A. That's what this is showing right here. And the outer conductor has a radius of B. The capacitor is the length capital L. And so I have to follow the process again. One of these is going to be plus Q, the other one minus Q. And so again, I first find the electric field, then the voltage, then the capacitance. The same 3 steps, but with different details. So here's my Gaussian surface. I pick a cylinder to enclose the inner cylinder there. I have to use lowercase l because I already used capital L for the length of the entire capacitor. So I'm going to use just for length of, you could have used A or something, no, not A, maybe like C or something. Doesn't matter, some symbol for the length of the Gaussian surface. So here's Gauss's law written out. The left side becomes E times area. Remember that that's because the Gaussian surface is, when you open it up as a cylinder, it becomes a rectangle, and it has dimensions of the circumference 2 pi r times the length. So 2 pi r times length, that's the E times area of this surface here. And then the Q enclosed is going to be lambda times the length, the coulombs per meter times meters. So I take the total charge, divide by the total length, and that's the lambda, and then I multiply by the length of the Gaussian surface. That tells me the Q inside the Gaussian surface, all over epsilon 0. The little l goes away of the Gaussian surface, and that gives me the electric field there. So again, why do we want the electric field? We got to do C equals Q over V, so we need to find voltage next. Okay, so that's found by, once again, minus the integral of the electric field from one point to another. So we integrate in, starting at B and integrating into A. B to A of our electric field expression, and the minus sign is still there. Now, dr over r integrates to natural log. All our constants are still there. We plug in the limits, log of a minus log of b, but then with this minus sign, the log of b becomes positive and the log of a becomes negative. And so the log of b goes in the top b goes in the top when we combine the logs. So there's the voltage, okay? And now, once again, we have to use C equals Q over V for the last step to get the capacitance. So C equals Q over V, there's the Q in the top, and there's the voltage we found over here. The Q's go away, as always, when we're deriving these capacitance expressions. The 2 pi epsilon 0 L goes to the top, and then the log stays in the bottom. And there's the capacitance for a cylindrical capacitor. All right, we're almost there. The last thing for today, dielectrics. So remember that atoms, matter, affects the electric field. All the calculations we've been doing for electric field, kq over r squared, Gauss's law, the distributed charge information that techniques we learn, it assumes that the charge is surrounded by a vacuum. But if it's surrounded by atoms, like the air, or maybe oil, or wax, or something like that, if the charge is surrounded by atoms, the atoms affect the electric field. How? Well, this is an atom without an electric field. We got a pluses in the middle, that's the nucleus of the atom, and then out here we have what in chemistry they call the electron cloud. It's like basically the electrons spread around evenly. And so when you're out here, this creates no electric field, okay? But if you put that atom in an electric field caused by some external source, oops, I forgot to put a parenthesis there, caused by some external source. Maybe I have a parallel plate capacitor like this, and we got positive over here, negative, and so it's making an electric field pointing that way. Now here's the atom. What happens is the protons, the nucleus of the atom, feels a force in the direction of the electric field. It displaces to the right slightly, and the electron cloud feels the force because it's negative in the opposite direction of the electric field, so it kind of distorts the cloud a little bit. So more of the minus is here, and that makes the atom a polar atom. It polarizes it, and therefore the electric field inside the atom points from plus to minus. It points this way. So the atom creates its own electric field opposite the electric field caused by the external source. When you add these two together, you get a net electric field that's been reduced slightly. So an example, this is 10 newtons per coulomb, this is 2. The answer, the net effect of the atoms and the external is not 10 or 2, but 8, right? And it's reduced. How much does this happen? Well, it depends on what material you're dealing with. Those are experimentally determined, and the amount, and we factor that in with what we call dielectric constant. Kappa, this is not a K, it's the Greek letter kappa from the alphabet, just like sigma, rho, mu, those are all from the Greek alphabet, so is kappa. And what you do is you put it in front of epsilon 0, and then you do all your electric field calculations, Gauss's law, distributed charge, the same way. The only difference is everywhere there's an epsilon 0, you put a kappa in front of it. And kappa's dielectric constant greater than or equal to 1. For example, kappa of air is pretty close to 1 because the air is not very dense. It doesn't create much reduction in the electric field. But if you use like wax or something, then that has more of a reduction in the electric field, so kappa is greater than 1 in that case. So the electric field is reduced by a certain factor. Okay? This is the original electric field divided by kappa. One final little piece here. The AP also wants you to be able to figure out how the dielectric affects capacitors when you put the dielectric into it. And there are two situations. One, the capacitor is isolated. I charge it up, and then I disconnect the battery, and I have positive and negative charge, Q and negative Q, on the two plates of capacitor. When I insert the dielectric, I didn't draw it, but I put the dielectric in, the charge doesn't change because these plates are isolated, so the charge can't like leak off anywhere. So the charge remains the same, but the electric field is reduced for reasons that I explained earlier. So that's the electric field reduced. That means the voltage is reduced also. Remember, voltage is electric field times distance. And the distance here doesn't change. And if the electric field goes down and distance stays the same, the voltage goes down from V equals E times D. And then from C equals Q over V, with a smaller voltage, we have a greater capacitance. So putting a dielectric increases the capacitance of the capacitor. And then also from U equals 1/2 QV, you see that with the same charge, less voltage, we have less energy in the capacitor once the dielectric is inserted. So you lose some energy. If the capacitor remains connected to the battery, then things are different. The voltage stays the same. It does not reduce like over here. Why does it stay the same? Well, the battery is keeping the voltage the same. That's what a battery does. It maintains a voltage. That means the electric field cannot change. This trips a lot of students up. They say, wait a minute, I put a dielectric. Doesn't that mean the electric field goes down? Well, only if the charge is isolated. But the battery maintains the voltage, therefore from V equals ED, you have to maintain the same electric field. How does that happen? The battery pumps out more charge into the capacitor plates. So the charge increases. That's how the electric field stays constant. But the capacitance still goes up from C equals Q over V, more charge, more capacitance. And the energy increases also from U equals 1/2 Q times V, more charge, more energy. Okay, so that's what happens. And that energy comes from the battery. So that is conductors in equilibrium and capacitors. Again, just a summary, we looked at some properties and behaviors of conductors in equilibrium, what happens to the electric field, the voltage of a conductor in equilibrium. Also, this effect of how conductors shield electric field from effects from they create shielding. We learned about capacitors, the general view, how to calculate capacitance for parallel, spherical, and cylindrical capacitors, and then also dielectrics. Okay, what the effects of matter are. So that's it for today's review. I just want to re-emphasize that you want to be studying this material and trying to master it before you begin working on your problems. If you are doing your problems with your notebook and these notes sitting in front of you and say, okay, how do I do one? Well, let me go look back at the notes. Okay, that's how you do it. Okay, let me try number 2. And then you go back and look at the notes to figure out how to do number 2. You are not training for the AP. Okay? It's like basketball practice. If you never practice doing the whole thing, transitioning from offense to defense, not talking to your coach every 3 seconds, taking breaks like you do. If you don't practice the game situation, you're not going to do well. And the same thing goes here. Practice the homework without your notes. Try and recreate the situation of the AP. So look at these notes, study them, try and master them, put them away, and then try and do the problems just from your mind, your memory of what the concepts and procedures are. All right, so that's it, and I'll see you for the next review lesson next time.